Now I'm very happy to invite him, and let me introduce him with a short biodata of him. Dr. N. Ponpandian is acting as a professor, is working as a professor and head in the Department of Nanoscience and Technology, Bharathiar University, Coimbatore. His main research focused area is water splitting, supercapacitors, sensors, solar cells, and he taught physics of nanomaterials, nanoelectronics, uh, and nanophotonics, environmental sustainability of nanomaterials, nanomagnetism. So he had vast research experience, 25 years of research experience and 17 years of teaching experience. His research credentials, his H index is 61. Citations, he had 12,882 citations, and I10 index is 197. So he had granted almost three granted patents and one filed, four filed patents. So publications, he has innumerous number of publications, more than 140 publications in books, various book chapters. He had done 23 book chapters and national journals, as well as publication database conferences. So he had attended many conferences and gave invited lectures. So he had almost 17 years of postdoctoral experience from 2014, from 1999 to 2008. He has done as a postdoctoral research at various institutions like University of Madras, Indian Institute of Science, University of Rostock, Germany, Free University of Berlin, Germany, University of Madras, once again, University of Nebraska, Lincoln, USA. So he had vast experience as a postdoctoral researcher. Uh, designation at Bharathiar University, where he had acted as a various designation. So first he joined as a reader in the year of 2008 at Bharathiar University, and then he promoted as a associate professor in the year of 2011 to 2014. Then he now from 2014 to till date, he is working as a professor in the Department of Nanoscience and Technology at Bharathiar University. So he had done a Doctor of Science in the year of 2024. He did his PhD at University of Madras in the year of 2003, and he has done MSc and MPhil at Sivagasi Ayanadar Janagimmal College. So projects, national level projects, ongoing projects is three. He has completed 13 projects. Uh, Ongoing is three for MSc and MSc level projects. And research guidance, he has completed 17 postdocs and 17 PhDs and postdoc three postdocs, and ongoing five PhDs and one postdoc. So at the institution level, he acted as several responsibilities, several committee members as well as coordinator. So director IQS, internal quality assurance committee, controller of examinations, senate member, standing committee of on academic affairs. So the various responsibilities he had done at university level, that is Bharathiar University level. So he acted as a visiting scientist in the Institute of Experimental Physics, Free University of Berlin in the year of 2006 to 2003 to 2006. So collaborative, he had many collaborative works under various from various institutions like Defense Metallurgical Research Laboratory (DMRL) and Indira Gandhi Center for Atomic Research and Center for Nanotechnology, Pondicherry University, and Central CSAR Secretary, then Nuclear Physics Department of Madras University, and Department of Material Engineering and Indian Institute of Science. So he organized many of the national conferences, workshops, and this ATAL ATP like program. He had conducted many programs like workshop, professor course, summer training program, internship program, like that. So 22 number of programs have been he coordinated as well as conducted. So this one of the uh, main channels he published is Applied Catalysis B Environmental uh, as well as Nanoscale Advances. So these are all his biodata. So it's a brief one. So I'm very happy to introduce him. So thank you very much for accepting our invitation to present a lecture on nanomaterials. So thank you very much, sir. Now I given the session to you, sir.
Thank you, Ponpandian sir, and for participants and co-coordinator and everyone. I want to mention that Ponpandian sir is out of station and with some busy and tight schedule. With this, he accepted and take all the pain and ready to give the talk today. Simply, he may say that today is not possible, but he tell that I will try and I will definitely do that. How can we do? And all the possibilities he tried, and now he is with us. Thank you very much, sir, for your commitment. Uh, that shows your seniority and your sincerity, sir. Thank you very much.
A very good evening to all of you, respected Professor Dr. Adimulam and his colleague, and all the participants and all the organizers for giving me the opportunity to deliver my lecture in this ATAL FDP. Today, my lecture is actually as per the schedule. It's nano composite material. This is also like a nano composite material. This is a 2D nanomaterial that is pioneering the future of green energy technologies. That is a sustainable green energy technologies. I'm mostly going to concentrate on the material aspect, even though in the intermediate slide, some of the slides, we are working on the energy based application. This material we are applying for the energy based application, especially for the water splitting application. You all know that the hydrogen energy is one of the important source of energy uh, in the modern world, because the energy requirement in the world is keep on increases day by day. But for example, today if we are using 25 terawatt power, and in 2050 we need almost to double the power, that is 50 terawatt power. In that way, we need some alternate energy sources. For that, we need to create some sources. One among them is actually the hydrogen energy. There is a clean and green energy. In order to make the hydrogen production from the water, we are using several catalysts. For that, we are working on tungsten oxide based some composites. That is a 2D material, and some other 3D and one dimensional material also we are working, but I'm going to concentrate here on 2D materials. Okay, you all know that the nanotechnology, in the material aspect, there are four different types. One is a three dimension, another one is two dimension, one dimension, finally the zero dimension. I am going to focus here only on 2D nanomaterials today. Okay, this you can see this slide. The energy, there are fossil fuels. These are actually the major sources of energy. Among that, in the non-renewable energy category, there are something, and again renewable energy. In the non-renewable energy sources, you all know that there are big problem in the future. Maybe after few years, the petrol and diesel, this kind of things vanish, almost vanish. In that way, you need to find out. Otherwise, the cost wise, it is much expensive. You all know that the cost of the petrol and diesel. And again, another problem with this kind of fuel is actually the environmental pollution, carbon dioxide and carbon monoxide. Again, in the renewable aspect, there are some sources, but those are also limited. The hydropower, that is limited with the water, the wind power, that is limited with the wind. Again, the atomic power, that have their own limitations. Again, thermal power, that also have their own limitations. In that way, everyone, the renewable energy sources have a lot of limitations. In that way only, we need to find out the alternate energy source. One among them is to produce the hydrogen from the water, that is a clean and green energy sources, because the precursor in this particular process is a water. Again, the end product also become the water. In that way, this is a clean and green energy, and this is sustainable. We need to produce a sustainable energy for the future. You all know that now everybody is talking about the word sustainable. The UN also have declared 17 sustainable development goals. Among that, one is actually the clean and green energy. That is another important thing. For that, everybody is interested to work in recent days. Here, these are actually the major renewable energy resources: solar, thermal, wind, wave, hydropower, and biomass. In the solar energy, you all know that the limitation is with the efficiency. You are using the silicon based solar cell that can able to convert only 20% of the sun's energy to the electrical energy. But again, there are certain new materials, then smart materials available to make a solar cell, that is perovskite solar cell. You all know that the stability is the matter. Even though it give more than 40% efficiency, but the stability is not much. In that way, it is not. It is still in the laboratory scale, not in the commercial scale. And again, you all know that based on the cost, we are producing some other kind of solar cells. That is a dye-sensitized solar cell. Again, their efficiency is a matter. Thermal power, we don't have a coal. There is very limited source of coal. Again, pollution is the biggest one. Wind, I have already. Wave energy also, there are not enough technology to make the energy much higher. Hydropower is also limited. Biomass also limited with there. And again, these are actually the motivation to make this kind of energy source. You know that the solar is the only renewable source that capable of providing 20 to 50 terawatt of power worldwide. We need now, till now we are using only till 2021 we are using 18 terawatt. So now it is increased again, around more than 20 terawatt we are using. In the worldwide, you can see these are the potential to make a different type of power. From the wind we can create 4 terawatt. From the biomass we can able to generate 5 terawatt. Hydropower only less than 1.5 terawatt. And again, for the geothermal, it's less than 1 terawatt. Solar, you can see 1,20,000 terawatt. But we don't have a technology to create that power through the sunlight. In that way, we need to have another technology. For that only the water splitting. Here also, the sunlight can be used. The energy from the sunlight that can be used to split the water to get the hydrogen and oxygen. Because our prime minister also announced from 2 3 years back, he has announced that the trains which running in our country is actually working based on the hydrogen energy in the future. That is what he declared some 2 years back. Now there are so many hydrogen production companies are evolving in Tamil Nadu and in the state of Gujarat. There are already some companies are there to produce the hydrogen, and in that way there are so many hydrogen vehicles are already started running. In that way, we are already utilizing the hydrogen, but we have to do much more in this kind of aspect. For that, in order to improve the efficiency of the hydrogen production, we need to have some good material also. That is another important thing. That material only catalyze the activity, and in that we can able to get the good hydrogen energy. Here, these are actually the vision for storage. Here, this is fuels. One is here. This I already mentioned. This hydrogen energy is a clean and green energy. We are using the sunlight and to put the water. This is electrochemical water splitting. Here, what we are doing is that we are the catalyst is actually some kind. Previously they are using the noble metal as a catalyst. You all know that the problem with the noble metal, gold, silver, platinum, this kind of ruthenium, iridium, and this kind of material, there These can be used as a catalyst. You all know that the problem with this kind of material cost wise, it is much expensive, even though it will give good efficiency. In order to replace that material, we need to find out some material to catalyze this particular reaction. Here, the advantage here is you don't need any wire connection or any external electronic to split the water, and it will provide the we can use the low-cost semiconducting absorber, that is a catalyst to split the water into hydrogen and oxygen. And again, it is a direct energy storage in electrochemical bonds. We are splitting the electrochemical bonds between hydrogen and oxygen to get the hydrogen. And again, the hydrogen for fuel cell, that again that can be used for in this hydrogen, the produced hydrogen can be used in a fuel cell to run the vehicle. And again, it is a closed to loop cycle, because the initial starting precursor is a water, and again the end product also become the water. Again, only there is a small disadvantage, that is actually difficult to find right materials, and again the in the right scale. That is a problem. For that only we have to work to get the better efficient material. This is actually the hydrogen and the fuel cell technology. You can see in combustion process, when you put the hydrogen, two hydrogen atom and oxygen molecule, you can get two water molecule plus hydrogen, two water molecule plus hydrogen as a catalyst. And again, in fuel cell, what we are doing is we are putting two hydrogen molecule together with oxygen molecule. In that way, you can get water plus electricity. This is in the combustion process, you will get water and heat. Here in the fuel cell, you will get water and electricity. That electricity will run the vehicle. This is a fuel cell setup. Here also in the fuel cell, this is actually a clean energy process. No greenhouse gas emission will not take place. Again, no air pollution, and again it will give the improved energy efficiency during the reaction. Why do we need a hydrogen? That's what this particular slide. For example, the climate change. In the fossil fuel, you all know that when you are using either petrol or diesel, or in the thermal energy coal, there is a lot of emission of carbon dioxide and carbon monoxide. In that way, the climate will be this environment will be polluted. You all know that during the corona, we are reduced using all these fuels. In that way, the environment was actually clean. In the next consecutive year, you can see there are a lot of rain. That is actually because of the pollution, reduced pollution. In that way, you can reduce when you are using this kind of hydrogen, you can reduce the pollution. That is the first thing. Again, another important thing is the reduction in the fossil fuel production. Fossil fuel you cannot able to produce after a long time. Maybe only few years it may be available. After that, there will be a deficiency in the fossil fuel. For that, you need to find another source. And again, what is be done when with the hydrogen? When you are using the hydrogen, you can make the environment in a much cleaner aspect. Again, it will give the hydrogen will give the clean energy, renewable resource, energy storage also possible, hydrogen storage also possible, but there are certain limitations here also. The limitation here is, you all know that the hydrogen is a lightweight gas. In that way, you need a very large volume to store the hydrogen. Only even 1 liter of hydrogen you wanted to store means you need a very large volume. The storage is a problem, but we have to make certain material, some porous material to store the hydrogen. In that way, you can use the hydrogen for long. Again, versatility, reducing emissions that I already explained. Again, energy security, technological advancements, again, the government support. You all know that the solar cell, we are installing solar cells in our houses based on the government subsidy only. Otherwise, the cost wise, the solar cells are much expensive. Like that, in the initial stages, the when you are making the hydrogen, That also little difficult because it is a little costly one, and you cannot you may not be affordable for that. The government has to give some support to make this particular technology for it to everyone. In that way, the government support is also mandate. Next, now government is supporting not only to make these things, and again a lot of research projects also they are awarding in this particular area. In that way, you may also get some project. Okay, these are actually the different energy sources. The hydrogen energy, different kind of hydrogen energy sources with a certain how much amount of created. Again, the hydrogen have a lot of advantage. From the hydrogen, the energy can be released of 140 kilojoule per gram. It can, and again, in the heat of combustion, it will give only 34.18 kilocalorie per gram. Again, energy storage capacity per mole is around 119 kilojoule per gram. These are actually the methods of hydrogen production. These are actually the different types of hydrogen production. One is actually the fermentation. Using fermentation process, you can make a the first one is actually the natural gas reforming. From that also you can make a hydrogen. The next one is liquid reforming. Also you can make a hydrogen. Again, fermentation and electrolysis. We are doing the we are making the hydrogen using the electrolysis process. There two different process. One is a electrochemical water splitting, and another one is a photoelectrochemical water splitting. And again, there are some more sources also available. Even the temperature variation also you can do. Again, some more technologies also available. But these are few technology to make the hydrogen. The electrolysis, what the electrolysis process is here, this is here the water molecule. You can see using electrolysis process in the electric, when you are passing the electrical current through the water between the two electrode, that is a anode and cathode. That's a positive, that is a positive, and minus poles of a battery, that is a anode and cathode. The water is split into oxygen and hydrogen. Okay, in it is actually used in the industries, especially in making aluminum industries. There are two different types of water splitting. One is actually high pressure electrolysis, and another one is a high temperature electrolysis. In both the way, you can split the water into hydrogen and oxygen. Okay, to here you can see in the right side picture, you might have seen that that is actually the two water molecule that can give two hydrogen molecule together with an oxygen molecule. This is in water splitting. You can also that known as a water electrolysis. That's what I mentioned in the previous the electrolysis. Water electrolysis, that is a process. It's a chemical process. You all know that the electrochemical process that separate water into its constituent element. There are two constituent, hydrogen and oxygen. This also possesses a significant interest due to the potential of usage of clean hydrogen in the future sustainable energy technology. The next slide, you can see the overview of water splitting. You can in the water, maybe you can skip these things because I have to concentrate much on material. This is actually the entire setup, PEC setup. There is an anode and a cathode, and this is a, for example, there is a semiconductor. In the anode and cathode, we used the material, we used our catalytic material because my interest here, the lecture here is today is actually the catalyst. In that way, I just concentrate on catalytic material, where we are using those material and how it can be helpful for splitting the water. Here in the anode, both anode and cathode, because here there are when you are splitting the water, there are four different processes are happen. One is actually the hydrogen evolution reaction, and another one is oxygen evolution reaction, and two more are actually hydrogen reduction reaction and oxygen reduction reaction. In this way, HER, OER, HRR, ORR. That is oxygen evolution, hydrogen evolution, oxygen reduction, and hydrogen reduction. These four different processes can happen during the electrolysis process. Here, We are using the electrocatalyst in the anode, both anode and cathode. You can see here in the left side, here you can see this is actually in the semiconductor, there is a valence band and conduction band. Okay, here in the valence band, what exactly happening is in the if this is a working electrode, and the right side is actually the counter electrode. In the working electrode, we are using the some semiconducting material as a electrocatalyst. Here in the valence band, what exactly happening is there is a hole creation. In that way, this will give from the water. Water is electrocatalyst here. This water is electrolyte here. From the water, you can see there is a hydrogen ion plus oxygen. You will get the hydrogen ion plus oxygen. Again, in the conduction band, what exactly happening is there is an electron. Here you can see there is an electron is produced. In this electron will be put it into the circuit. In that way, you can produce a electricity. Again, in the counter electrode, what exactly happening is actually this is a different semiconductor, and here from the hydroxyl ion, it attract it react with the oxygen. In that way, it will give again the hydrogen. Okay, this is what the entire process. Okay, whenever this is actually in sometimes this will have a Hopsel reaction. In that way, that will produce only hydrogen evolution. In sometimes it can react one in one electrode, it will give the hydrogen, and other electrode it will give the oxygen. In that way, hydrogen and oxygen will be produced simultaneously. In that way, it will call it as a full cell reaction. In that way, you can get both hydrogen and oxygen. These things we can skip. These are again almost to the same thing. That's what is a half cell and full cell reactions. Maybe we can directly now go to the catalytic material. In that way only I can able to complete my lecture. This is actually the selection of our electrocatalyst. So how one can select the electrocatalytic material for this kind of application, because in order to split the water into hydrogen and oxygen, you need an energy of 1.23 electron volt. For that you have to, because when you are coating this particular electrocatalyst only, you can attract the sunlight, and that sunlight can give that particular energy to split the water into hydrogen and oxygen. Here you can see the first one is actually to tune the band gap. Okay, to tune the band gap. Okay, because the band gap is a very important one for the semiconducting nanomaterial. When you are tuning the how one can tune the band gap by changing the size, or you can add the doping elements. There are two ways. One, in the bulk you can dope other material foreign element. In that way you can change the band gap. But in the nanomaterial, when you can reduce the grain size to nanometer scale, or even less than 50 or 10 or 5 nanometer, you can easily tune the band gap of this particular semiconductor. That is the first way. You have to get the clear band gap for this particular application. The next important one is actually the electron transport property. You have to improve the electron transport properties. So there is a second. In that way also you can improve the efficiency of this catalytic material. And again, you can do one more thing, that is a hole in order to increase the hole diffusion length. In that way also you can improve the efficiency. And again, you can make a valence bandage. That is another important effect in this kind of this material that can be useful as that can be used as a catalyst in electrocatalysis. And another important thing is a chemical stability. That is another important thing, because we are coating this catalyst in the electrodes. There we directly put that electrodes in the water. There the stability is a major issue. In that way you have to have a better stability. And another important aspect is a cost effectiveness. Okay, the cost wise also it should be cost wise, and it should be earth abundant material. Then only it can be useful for any kind of applications. Okay, now you can understand these are the important properties to select the electrocatalytic material for this kind of applications. The first one is a band gap. Second one is actually that electron transport properties. Again, hole diffusion length. Again, valence bandage. Again, chemical stability. Finally, the earth abundant material. It should be earth abundant material and as well as the cost effective material. These are actually tuning the band cap. That's what I mentioned, tuning the band cap in the nanomaterial. You all know that when you are decreasing the grain size of the material, the band cap increases. Here, this particular application requires a range of band cap energy that should be around 2.3 or something, 2.3 electron volt or less than that. In that way only it can be useful for this kind of electrocatalytic application. These are again how one can tune the band cap. That's what I explained. Now I can come back to my topic here. This is what we are tuning the catalytic property of that material for our electrocatalytic applications. The first one is actually the morphological, that is actually the structural dependency. We are making the structural dependent materials. There we are, our choice of material is a tungsten oxide. The base material is a tungsten oxide. We are tuning the structural properties of the tungsten oxide. First, there is a there we are changing the structure from orthorhombic to monoclinic, hexagonal. In that way, we can tune the structure of this particular tungsten oxide. In that way, also, you can improve the efficiency of the catalytic activity. Here, these are studies on the crystal structure of tungsten oxide for hydrogen evolution reaction. Again, what we wanted to do is again the tuning the morphology, the morphological tuning of tungsten oxide nanostructure for hydrogen energy. For that, the next slide, you can go to the next. Here, what we are doing is we are making the first step. What we are doing is the basic is actually the tungsten oxide. In addition to the tungsten oxide, what we are doing is we are adding some 2D materials. That is actually the graphene. Graphene is a 2D material. You all know that the carbon, based on the allotropes of carbon, you can get 4 different types of nanomaterial. I hope you all know that. There is a first example for 3-dimensional carbon is a graphite. That is a 3-dimensional structure. From that, if you remove one layer of carbon from the graphite, that will give the graphene. That is a 2-dimensional material. Now, this 2D material, you can fold it in that way, you can get a nanorod or nanotube. In that way, you can get a 1-dimensional carbon nanotube or nanorods. And again, from that graphene sheet, you can make a carbon dots. That is a 0-dimensional material or quantum dot. Okay. In that way, using carbon, you can make 4 different types of nanomaterial. We are using the 2D material, that's a graphene, for our application to make the composite. Now, what we are doing is we are making the composite with that particular tungsten oxide, adding graphene with a tungsten oxide. Here we have used 2 different graphene oxide. One is a general graphene oxide, another one is a reduced graphene oxide to make the composite. In that way also we are improving the efficiency of that nanomaterial. And again, the next step, what we are doing is, in addition to this particular composite, what we are doing is we are making some decoration with a noble metal. We are using gold as a noble metal to decorate for this particular, but in that way also we can further improve the efficiency, catalytic activity of this particular material. What we have done is we have took the tungsten oxide as a base material, then we added the graphene, that is a 2D material. Again, we have decorated with a gold nanoparticle. In that way, we are improving try to improve the efficiency, catalytic efficiency of this particular nano composites. Now you can see here in the tungsten oxide, the next step, we are making a different type of composite. Here what we are doing is, in addition to the tungsten oxide, we are adding or doping some rare earth elements, that is europium, cerium, like that. That's europium, gadolinium, and this kind of rare earth element we are adding with a tungsten oxide. In that way also we can tune the band cap of the tungsten oxide. In that way we can improve the efficiency of that particular material. Here the lacking is the different rare earth materials dopant, and their reason we can learn it in this particular process. Here you can see the we can do the co-doping. Okay, for example, we are doing here, what we are doing is actually, in addition to tungsten oxide, in the previous one we are doping up rare earth elements. Now here what we are doing is we are doping up actually graphene oxide with some uh, another dopant elements with the graphene oxide, sulfur, phosphorus, like that. We are adding in that way. Also, we can improve the efficiency of that particular material. In addition to that, with the tungsten oxide, we are also adding the transition metal, that is iron, cobalt, and nickel. And in addition to that, iron cobalt together, and again iron nickel together, again cobalt nickel together. In that way also, we are making the better composite for this particular catalytic activity. These are actually our objective to make the better materials. The first one, we wanted to tune the morphology of the tungsten oxide with the three different morphology. One is a one-dimensional structure, another one is a two-dimension, and again three-dimension, and finally the zero dimension we are not unable to make with the tungsten oxide, but we have made three different dimension, 3, 2, and 1 dimension using the tungsten oxide. Next one, can you click one more? Okay, now we can characterize the material with a different characterization techniques, and again in that way all the physicochemical characterization will be done for this particular material. The objective 3 is to make the electrochemical hydrogen evolution reaction studies. For that we are tuning the morphology instead of morphology, and again the next objective, to make the oxygen evolution reaction in the electrochemical oxygen evolution reaction. For that we are making some other material based on tungsten, co-doped tungsten oxide, in that way with iron, cobalt, and nickel. Next one, the objective again 4 is actually the OER. Again the objective 5 is photoelectrochemical water splitting, again finally with a full cell reaction. Here we made some device to make a full cell reaction. There one cell will produce hydrogen and another cell will produce oxygen. In that way, when you are splitting the water, you can able to extract both oxygen and hydrogen to for the commercial purposes. Here you can see, this is what I explained, how one can make this morphology. The second objective is a binary nanocomposite, that is tungsten oxide with carbon, that is a graphene. Again the ternary nanocomposite, there actually the tungsten oxide together with a graphene and gold, and again the doping, the rare earth, again co-doping the transition metal. These are actually the material which we have prepared for our application. You can see the morphology. These are actually the different preparation techniques for preparing the different morphology of the tungsten oxide. You can see all the basic elements, the precursors material. When you are heating the precursors with 500 to 550 degrees centigrade, you can get the tungsten oxide. These are actually the how one can get the one dimensional, two dimensional, and three dimensional. Zero dimension we are unable to prepare, it not succeeded, but all the other things you can see the table. You can get the protocol to produce the different types of tungsten oxide, three dimension, two dimension, again like a flower shape, and there is a different morphology, nano rod or nano wire, and these kind of morphologies you can able to produce with this particular protocol. And the next, and again we can make we can deposit this in a carbon cloth that can be used as a electrode. This prepared material, this tungsten oxide material with a different morphology, that can be deposited on a carbon cloth. You know that the carbon cloth have better electrical conductivity. In that way we are using that as an electrode, and that this material can be coated on that particular electrode for that further application aspect. This is what this particular slide explains. Then we always do all the physicochemical characterization of this that we can skip. That is a routine process. You can see the next slide. This is a routine process. That is the top one is actually which we have drawn that particular but the original image you can see the original scanning electron microscopic image. You can see all the 3, 2, and 1-dimensional structures. It's clearly visible. These are actually the scanning electron microscopic image of this 2-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional structure. Next, these are some basic characterization which always perform whenever we prepare the material. We can skip all these things. This everyone knows. Can you go to the next? And again, you can. These are actually the parameters which we derived from the structural factors, the grain size, and all those things. This also may be skipped. You can see the surface area of this different kind of morphology. You all know that the surface area play a vital role in this kind of applications. In that way, you can see the maximum surface area that can be obtained for the nano rod shaped sample. Okay, that's a 1-dimensional structure that will give the maximum surface area. You all know that again the catalytic activity also much higher in this kind of nanorod like structure. This can be used for the future applications to make the doping and all those things. This again the transmission electron microscopic image of those material. Skip. Can you go to the next slide, please? Okay, these are again some more characterization analysis of this particular binary nanocomposites. That is actually the this is actually the graphene again together with a tungsten oxide. Graphene with the tungsten oxide. You can see the rightmost picture. That is the image is actually the graphene sheet. Again, the tungsten oxide is deposited on the graphene sheet. You can see the tungsten oxide together with the graphene. Again, these are actually the characterization based on these particular binary nanocomposites for the XRD, Raman, and all those analysis. Here you can see the Raman spectrum that shows the graphene. This graphene is already there in this particular composite. Okay. Now the surface area also, you can see the surface area, how again how the band cap can be changing by for the different morphologies of this tungsten. For example, this is a tungsten oxide together with a graphene oxide, pure tungsten oxide, it is 2.69. For tungsten oxide with a graphene oxide, 2.71. With reduced graphene oxide, you can 2.64. Like that, you can see the different band cap is tuned. Like that, here in the bottom, you can see the surface area also can be tuned based on the different morphology and again different tungsten oxide compounds. These are again some more characterization of this particular. Again, this is a ternary nanocomposites. I already mentioned this tungsten oxide, graphene oxide together with a gold nanoparticle. And this is again the morphological structure of those particular material. Next, this again, this is surface area. We have measured the surface area of all those sample again composition and all those things we have measured through XPS, PET as well as the visible absorption structure. Now the next step, this is the first step we have done it. There is a first kind of sample that is actually the starting from tungsten oxide, again graphene and gold. Now the next step is we are adding, that is a doping rare earth, samarium, europium and gadolinium. In that way we are getting 3 different type of material. Here also we have studied all those properties. That is actually the structural, again the morphological analysis and all those things we have done. And because this material again, especially the gadolinium and all actually magnetic, because we wanted to improve the efficiency of catalytic activity through magnetic field also. For that reason only we are added gadolinium also in this kind of nanocomposite. And again in the next set in the 3D transition metal, you all know that iron, cobalt and nickel are magnetic. In that way we have added all together with some co-doping, iron, nickel and these things. Okay, these are again the same characterization technique which we have performed for this kind of rare earth dope materials. This is again the morphology of all the samarium, europium and gadolinium dope material. In that way you can see the difference in the morphology. The morphology also play a vital role when you are doing some electrical characterization of the material, not only size, because when you are reducing the nanopart size of the material, based on the size, the catalytic activity changes, but based on the shape, the electrical property change. In that way, you can see the electrical property that is changing here. And again, this is a transmission electron microscope, the scanning electron microscope, this is a EDAX of that particular sample. This is again some more characterization. This is a BET and XPS analysis of the rare earth dope samples. Now the next one is actually, you can see the transition metal iron, cobalt, nickel, in addition in co-doping. The iron cobalt together, iron nickel together, again cobalt nickel together, iron nickel together. In that way, we are making different electrocatalysts for the applications. Here, when the transition metal is doped with a tungsten oxide, this again the structural property changes. This will give much improved stability in this kind of catalytic material. In that way, we can make the better electrocatalyst. You can see these are actually some of the structural characterization of this particular material, the XRD and Raman analysis of this particular material. Next, this is again the morphological analysis, how it can be the ion transition metal, codope tungsten oxide electrocatalyst. Here, these are the morphology. This first one is tungsten oxide with iron cobalt. This is again tungsten oxide with iron nickel. The last one is tungsten oxide with iron nickel. We got a best electrocatalytic activity for the iron nickel sample, because you all know that the nickel is a very good electrolyte. When it joined with the iron, that also give much improved electrocatalytic activity. This is a transmission electron microscopic image of again this particular transition metal codope. This is again the surface area analysis of this particular material. Again, the surface area here also much higher compared to the codope sample. In the case of iron nickel, the surface area is maximum. In that way, the catalytic activity of that material also is maximum. And now we wanted to use this material in this particular electrocatalytic splitting the water into hydrogen and oxygen. Here you can see the picture. In the right side picture, you can see how the oxygen evolution reaction taking place. And again, in the first quadrant, generally the oxygen evolution reaction. In the third quadrant, you can see the hydrogen evolution reaction taking place. In this particular graph, you can see here, this is an electrode. This OER happen in this particular full cell setup. One side there is an oxygen evolution reaction that is in the anode. In the cathode, you can see there is a hydrogen evolution reaction happen. Okay, here this reaction again depends upon the catalyst, again their catalytic property of this material, because some of the material only can applicable for making the oxygen evolution reaction, and some other material that can be used to make a hydrogen evolution reaction. In that way, the tuning, the getting the best electrocatalyst for both the reaction is a mandate. For that only we are tuning the properties of this particular electrocatalyst. Okay, maybe with this I can stop it. If you have any questions in this kind of material or preparation, you can please.
So thank you very much for the presentation, nice presentation, sir. In spite of your busyness as well as I think you are some physical illness now. So thank you very much for the nice presentation, sir.